With this process, we're controlling the speed of a pneumatic air motor. This is a pneumatic drill mechanism. We're spinning a generator to measure the speed. A generator is sending a signal over here to the input of a process loop controller. The process controller is sending an output signal to an IDP, driving an air valve open and closed, which sends compressed air from our supply to the motor. So we're actually doing loop control with an airspeed motor. And you can see here as I increase the set point automatic mode, the process variable does come up. One of the problems we're facing though is it seems to be kind of sluggish in response at the top end, but over-responsive at the bottom. You know, as we go down towards the bottom end, it has a tendency to oscillate really bad. If you go at midway, it's even worse here. It tends to stabilize more towards the upper end and be more reactive towards the bottom. This is an example of a process that has a non-linear process gain. Down towards the low end of operation, it's extremely responsive. At the upper end, it's not so much. One of the reasons for that is our control valve here does not have an equal percentage trim. It has a linear trim, which means there's some distortion in its characteristic towards the bottom end of its range. As we go down towards the closed position, you notice the valve's closing off, the pressure drop across the valve increases, and as the pressure drop across the valve increases, it becomes more responsive. The same amount of stem motion has a greater change in flow rate than before. Towards the top end of the range, what we see here is that the process pressure across the valve decreases, so the same amount of valve motion does not produce the same amount of change in flow rate. So we have ourselves a nonlinear process. This can be greatly helped if we were to put in a valve with an equal percentage trim, which will tend to negate that process distortion. Until then, until we get a valve with the right trim, we'll do the best we can with tuning, our best compromise. We can turn down the gain a little bit, from 1.56 down to, let's say, 1.18. We'll store that. And here, not going to oscillate quite as bad at the bottom. Of course, the sluggishness at the top will be worse. But for now, we're just going to have to live with that, and that's less of a problem than having oscillation at the bottom. Another thing we can do, potentially in the future, is use something called adaptive gain. We can program the controller to change its own gain up and down as our range changes. It's kind of a crude fix to this nonlinear gain problem, but that is something we can do. This controller does give us the capability to do that.